Hey guys, so in this video we're going to learn how to find the volume of revolution or the volume of rotation of a function about the y-axis. And to do that we're going to try and solve the following problem, which says the diagram shows part of the curve with equation y is equal to x squared plus 1. So we have this part of the curve with equation y is equal to x squared plus 1. The shaded region enclosed by the curve, the y-axis, and the line y is equal to 5 is rotated through 360 degrees about the y-axis. Find the volume obtained. So when we rotate this shaded region 360 degrees about the y-axis, we get the following shape. And what we want to do is we want to find the volume of this shape over here. Now we want to find the exact volume of this shape. But in order to do that, let's first try and find an approximate value for the volume of this shape. And we can do that by dividing this shape into the stack of disks as I've shown over here. So what I've done here is I've divided this shape into 4 disks of equal height, and we can find the volume of each of these disks and add up the volumes to find an approximate value for the volume of the shape. Now we can calculate the volume for each of these disks by using the formula for the volume of a cylinder, that is V is equal to pi r squared h. And the height of each of these disks is 1 unit, since the height of this shape over here is 4 units from y is equal to 1 to y is equal to 5, and each of these disks has height 1 unit since we have 4 disks. So the first one is from 1 to 2, the second one is from y is equal to 2 to 3, and so on. But the radius of each of these disks varies. The radius of each of these disks is the x-coordinate on the curve over here. So what we want to do is we want to find an expression for the x-coordinate in terms of y. We want to find an expression for the radius of each of these disks in terms of y. So really, first we're going to find x as a function of y. Now we have the equation for the curve, that is y is equal to x squared plus 1, and here we want to make x the subject. We have y is equal to x squared plus 1, and if we subtract 1 on both sides, we get x squared is equal to y minus 1, and therefore x is equal to the square root of y minus 1. We don't need to take plus or minus the square root because we know the radius will always be a positive value. So this is the expression that we have for the radius in terms of y, that is the x coordinate on the curve. We can see that over here. The radius of each of these disks is the square root of y minus 1, that's the x coordinate, and the height of each of these disks is 1 unit. So we can use the following expression to calculate the total volume of these 4 disks. So for the first disk, the center is at y is equal to 1. So we know that the radius is simply f of 1, that's the square root of 1 minus 1, so that's 0. So then the volume of the first disk is pi times f of 1, the whole thing squared, that's r squared, times the height, which is 1 unit. For the second disk, the center is at y is equal to 2. So then we have pi times f of 2, the whole thing squared. Again, that's r squared times the height h, which is 1. For the third disk, the center point is at y is equal to 3. So the radius is f of 3. So again, we have pi r squared times h. And for the fourth disk, the center point is at y is equal to 4. So we can use the following expression to find the volume of the fourth disk. And if we add up the volumes of the 4 disks, we get the volume as approximately 18.84 units cubed. Now, of course, this estimate is an underestimate because the volume of the 4 disks is lesser than the volume of the shape. The reason why is because we're excluding the spaces between the boundaries of the shape and these disks here. Now we can get a better estimate for the volume of the shape by increasing the number of disks. So here I've doubled the number of disks from 4 disks to 8 disks. And if we add up the volume of these 8 disks over here, we get the volume as approximately 21.99 units cubed. And again, this volume is an underestimate because the volume of the disks is lesser than the volume of the shape, since we're excluding this volume between the boundary of the curve and these disks over here. So then, more generally, we can say that if we had n disks, the total volume for those disks can be given by the following expression. The volume of each disk is pi times r squared, so that'll be f of y, the whole thing squared, times delta y, and delta y is constant because each of these disks has equal height. So if we add n disks of equal height, this following expression will give us the total volume of those disks. And we can simplify this expression by factoring out pi over here. So if we factor out pi, we get the following expression. So in the first example, n was equal to 4 since we had 4 disks, and the height of each of those disks was 1 unit, that's 4 divided by 4. In the second example, we had 8 disks, and the height of each of those disks was 0.5 since we had those 8 disks spanning a height of 4 units. Now we know that if we increase the number of disks n, we get a better and better estimate for the volume of the shape. So as n approaches infinity, as n gets larger and larger, as we increase the number of disks, we know that the height of each of those disks gets smaller and smaller. The greater the number of disks, the smaller the height. So as n approaches infinity, we know that delta y approaches 0. And then we can say that If we have an infinitely large number of disks, if we have a very, very, very large number of disks, each of which has a very, very, very tiny height, like a height almost equal to 0, we can say that the sum of the volumes of those disks is equal to the volume of the shape obtained. And that volume can be calculated using the following expression. Here what we have is we can say that the volume of revolution or rotation about the y-axis is v is equal to pi times the integral from y is equal to a to y is equal to b. So in our example, that's from y is equal to 1 to 5 of f of y, the whole thing squared, with respect to y. Here, if we look at the expression for the volume of the n disks, we have pi times the sum over here. As n approaches infinity and delta y approaches 0, we know that the height delta y can be written as dy, and this infinite sum in the parentheses can be represented by this integral from y is equal to a to y is equal to b. So we have pi times the sum, that is pi times this integral, that will give us the volume of revolution about the y-axis. Here, the volume v is equal to pi times the integral of f of y, the whole thing squared, that's r squared dy, that's the height. So then let's evaluate this integral to find the volume of the shape. We can say that the volume v is equal to pi times the integral from y is equal to a to b, so that is from y is equal to 1 to y is equal to 5 of f of y, the whole thing squared, so that is the square root of y minus 1, the whole thing squared, with respect to y. Here the square root of y minus 1, the whole thing squared, is simply y minus 1. So we're integrating y minus 1 with respect to y. So we can say that v is equal to pi times the integral of y minus 1 with respect to y. The integral of y is simply we increase the power by 1, so we have y squared, and we divide by the new power. So we have pi times y squared divided by 2, and the integral of 1 is simply y. We're going to evaluate this from y is equal to 1 to y is equal to 5. So when we substitute the upper limit over here, we can say that v is equal to pi times what we get for the upper limit. So that'll be 5 squared divided by 2. That's y squared over 2 minus y, so that'll be minus 5. And we're going to subtract what we get for the lower limit. So that'll be 1 squared divided by 2 minus 1. And if we evaluate this exact volume here, we get v is equal to 8 pi units cubed. So we can say that the volume of revolution or the volume of rotation of the curve y is equal to x squared plus 1, 360 degrees about the y-axis, is 8 pi units cubed.